Hello, welcome to this class of Power System Protections. My name is Francisco Gonzalez, and the class today is related with conventional instrument transformers, starting with the classical current transformer, then the voltage transformer. I have included few slides about non-conventional instrument transformers and some other transducer. Okay. Before I start this class, I would like to remind you, please, if you want to have a copy of those slides, you just need to go to ResearchGate and find my project system protection, power system protections, and you can download the slide from there. Also, this class includes few examples. I create some MATLAB scripts that you can download from my GitHub. Please go to the repository named Power System Protection. Also, this teaching material have been improved a lot. I would like to express my gratitude to Brett Roberts from Ausgrid, Australia. He has made many good questions regarding how to improve the quality of this teaching material. Okay, what is the objective today? Well, today I will go across several topics, but the idea is to present a general introduction about conventional and non-conventional instrument transformers. Okay. The agenda today is a bit complicated. I will start with a short introduction about instrument transformers, and from there I will go to the first part, that is the conventional instrument transformer, talking about current transformer and then voltage transformer. At the very end of this session, I have few slides about non-conventional instrument transformer. Okay. Finally, there is a closing up, is a summary, some reference, and Q&A. Okay. Well, let's jump into the topic. To be honest, current and voltage transformers, they has been application in power system for many years. However, it's quite interesting topic, and we must be clear that voltage and current transformers, they are very specialized area. Okay. In this case, we are not going so detailed. I mean, this is a class that is not for deep understanding. It's not for a specialist. For that reason, I'm sorry if you are looking for that kind of thing. Okay. What I can say is many traditional and conventional current transformers and voltage transformers at substation, they exist and they will be there for many years to come. However, what we need to realize is that substations and the whole power system is changing. We are moving into a digital era where communication, information, they are very important topics. As a consequence, we are moving to fully digital substations, and that involves all the processes, monitoring, sensing, and of course protections. Okay, that is the moment that we start to use the famous IEC 61850. Okay, all my students, they must be aware that IEC 61850 is making a lot of change in terms of how the substations are built and how we need to project the future power system. Okay, what is interesting to say is that IEC and IEEE standards, they have changed over the time. I mean, they have been adapting for many years to the digital area. However, what we need to understand is that the technology for the primary equipments has been for many years in the market. Okay, we can say that probably the technology is evolving between 7 or 15 years. considering that the normal life of one power equipment could be 50 years. But it's very different from the digital area. If we start to think about firmware, software, and electronic relays, wow, the evolution has been extremely fast. Okay, well, let's go for main discussion about instrument transformers, or also called transducers. Okay, what is the idea of those kind of devices? Well, power systems, usually at substation level, we work with very big voltages and currents. I mean kilovolts and kiloamps. However, relays, power system protections, and some monitoring system, all of them, they work with very low voltages and very low currents. As a consequence, we need devices to transform the power, currents and voltage into levels that can be used for relays, protection relays, and for monitoring system. But also voltage and current transformers, they provide isolation. I mean, as you must be aware, transformer has a beautiful property that is creating the isolation between what we call the isolation between the primary and the secondary winding. Okay, at this moment, I just want to say that current transformers and voltage transformers, okay, primary and secondary, they have standardized values. As a consequence, we can find in the market them and allow the interchangeability between different components. Okay. However, what is interesting to say is that, for instance, the case of current transformer in United States of America, and also several other countries, the current transformers, they are standardized for a secondary current of 5 amps, and the situation is a bit different in Europe. On the other side of the Atlantic, here in Europe, we use standardized secondary winding, but the nominal current is only 1 amp. Okay, what is important to say is that those transformers, voltage and current transformer, the idea is that they must do the best effort to transform the signal, for instance, from short circuit faults of 100 km's to 1 amp, but it's not just reducing or decreasing the size of the amplitude of the current. It's also trying to replicate the current as best as we can. I mean, the idea is that we reproduce the primary quantities, but keeping all the features inside quality levels: amplitude, phase angle, wave shapes, harmonic contains, etc. Okay. Something that my student must be aware is every single instrument transformer, every single voltage and current transformer, there are some errors that they are involved over there, and you must be aware about that. Okay. Typically in power systems, we can see there are some in power system we have several voltage and current transformer. I believe you can see on the right hand side that is a classical substation bay. You can see this power circuit breaker. However, I highlighted over there the circuit breaker. There is a current going in and out, but also here we have some current transformer. And the idea is that the current transformer is connected in series. With the current and the circuit breaker, and the idea is to take the primary signal and transform into a secondary level that can be used for the relays or protections, okay? And on the other hand, we can identify in that figure, we can identify over there the potential transformer, called in some countries potential transformer or voltage transformer, but you must realize that the voltage transformer is taking signals or measurements between the line and what is the neutral or ground point, okay? Well, but let's jump into more details about current transformer. Current transformers, the idea is that they take the AC signal from the primary and transform into a current signal on the secondary. There is a transformer ratio, but the idea is transforming the signal, but at the same time providing isolation. There are many types of current transformer. Here I just present a very basic classification of current transformer. You can see the wand CT, the bar CT, the window CT, and one very specific case is the Gaussian current transformer, okay? However, something that you must be aware is, be careful. Every single current transformer can have a primary winding and a secondary winding or multiple secondary windings. But the important thing is, because those transformers behave like current sources, they never be connected in an open circuit. What I'm trying to say is always a CT must be connected to a load, okay? Let's jump into the first type. Here you can see the classical one CT. There is a primary winding and secondary winding, all of them connected by using magnetic field that is moving inside a magnetic core. If you look at the magnetic circuit on the right hand side, you can see that this is the similar configuration used for a power transformer, a two-winding power transformer. There is a current in the primary winding, there is a current on the secondary winding, and the interaction between primary and secondary is only based on the magnetic interaction using the magnetic core. On the other hand, here I can show you the bar current transformer. The main difference between the bar current transformer and the others is that there is a magnetic core, of course, but in this case there is not a primary winding like in the previous one. Here we have a single conductor, and this is the conductor that could be the bus bar conductor or a cable, and the current is moving over there. And you must remember that when the AC current is moving in a wire, you have a magnetic field, and that magnetic field in the space surrounding the bar or the wire is interacting with the magnetic core. In that magnetic core we have a winding, and that is the secondary winding. As a consequence, the bar CT is a very simple CT. However, the main difference is there is no specific primary winding, okay? Here I would like to show you just a basic scheme about the bushing type CT transformer. Some manufacturers, they identify the advantages of including the current transformer in the devices. For instance, it's quite typical that you can find in oil circuit breakers this range of bushing type CT. If you look over here on the right hand side on the top, you can see the real oil circuit breaker, and you can identify the location of the bushings. But below there is something like a cylinder that is present in the figure below, and the idea is that here we have the current moving inside, moving across through the circuit breaker, and on the top we have the current transformer. The idea is to produce an equipment that combines the functionality of circuit breaker, but at the time saving space and saving some money in terms of including external CT, is the use of the bushing type. Okay. Well, this is all about the different types of circuit breaker. In this course, we need to run some calculations about circuit current transformers, and the best way to understand this is starting with the classical steady-state performance of the current transformer. A current transformer, you will realize that is similar to the two-winding transformer. Here in the center of this slide, you can see the circuit equivalent model for a current transformer. You can identify that there is a lot of similarities between this model and the model used for the two-winding transformer. There is a primary leakage impedance, there is a secondary leakage impedance, there is a magnetizing branch, and to simplify the circuit, we include an ideal transformer between primary and secondary. And you can see here on the secondary the important and very important load impedance. Later we will call this load impedance the burden. Okay. What we have done is use just the basic theory about two-winding transformers, and we convert the equivalent model into a simplified model where all the quantities are referred to the secondary. Okay, the idea is make the calculation extremely simple and easy to see. All the quantities refer into the secondary winding. Here you can see there is a phasor diagram. In this case, we are presenting all the voltages and currents include inside this current transformer. Okay, what you need to understand is the magnetizing branch. There is a voltage across the terminals, and that voltage depends on the magnetizing impedance. Okay, in few slides we will discuss about this magnetizing impedance, because this magnetizing impedance is related with the magnetic properties of the core, the magnetic core, and we identify how important is considering that magnetizing impedance. Okay. Now what is really important for us for power system protection is identify that every single current transformer has indicators to define how good is performing the current transformer. In this case, I would like to introduce two of those indicators. One of them is called very simple. It's called the ratio between the magnetizing current and the primary current. That is what we call the per unit current transformation error. It's a number that allows us to identify how good the transformer is transforming the current from one side to the other. Okay, and another important element indicating the performance of a current transformer is what we know the ratio correction factor. Okay, the ratio correction factor is defined as a constant, and it's basically presented in the nameplate of any transformer, a current transformer, and we use the letter R and to identify this ratio current factor. If you look over there, the ratio correction factor is related with the per unit current transformation error, and the equation is extremely simple. It's presented over there. Okay. What I want to say is that if you know both of those factors, you have an idea about the performance of your current transformer when there is a load current on the secondary of the transformer. Okay? Well, I think it's time to be practical in terms of the steady performance of the current transformer. And now I would like to move to an example in order to see the calculation of the per unit current transformer error and the ratio correction factor. Okay, let's start with the following. Imagine that we have a current transformer. This is a very simple current transformer. Transformer ratio is 500 amps on the primary, 5 amps on the secondary. As you must be aware, this example is using an American current transformer, okay? We know that there is a secondary leakage impedance, and also we know the burden. The burden here is 2 ohms. As you can see, is a fully resistive burden, okay? Then there is a magnetizing branch with real and imaginary component, 4 ohms plus a 15J. Okay. Now, what is the question? The question is, first, calculate the per unit current transformer error, and second, calculate the ratio correction factor. Okay. Well, it's extremely simple. What we need to use is the equivalent circuit model. All the quantities are referred to the secondary, including the magnetizing impedance. And here you can see the numbers, okay? It's very simple to see that the secondary leakage impedance is in series with the burden, and there is a current I2 moving across them. And on the other branch, we have in parallel the magnetizing branch. As a consequence, it's extremely simple to see that this impedance here is in parallel with the series of those two over there. If we use Ohm's law, it's extremely simple to say that the magnetizing branch is the equivalent impedance multiplied by the primary current. If we put the number together, we get here the magnetizing, an expression for the magnetizing voltage in terms of the equivalent impedance and the primary current. But you must be aware there is a relationship between magnetizing voltage and magnetizing impedance. That is the famous Ohm's law. And if we use the result before and combine together with the Ohm's law, we can get something very simple, and that is the per unit current error, CT error, okay? Something that you must notice here is that the per unit current transformer error is independent of the magnitude created by the primary current. It's independent of the primary current because if you look the definition of per unit CT error, you will realize that that error is equivalent to dividing the equivalent impedance by the magnetizing impedance. What I'm trying to explain, what I'm trying to say is the per unit current error is not dependent on the primary current. And on the other hand, the per unit error is depending on the impedances of the model. Okay, I will take here just a few seconds, and I will try to use my I will. Okay, let me try to put in context what I am trying to explain. Okay, if you remember, the equivalent circuit, of the current transformer is defined by a magnetizing branch, yeah, and here we have and the burden here, okay. Okay, this is the total. This is the equivalent model. This is the equivalent model of the CT, and we can simplify the model in this way. Okay, Ohm's law say magnetizing voltage is equal equivalent impedance multiplied by the current. Okay, and however, what is interesting here is from this circuit we can say that the equivalent impedance is the parallel between the series of the burden and the secondary leakage, yeah, and the magnetizing branch. Okay, but what I'm trying to say here is, well, we have the equivalent impedance. The equivalent impedance is the parallel between this series and the magnetizing branch. But if we come back to the definition of the per unit, if we go back to the definition of per unit CT error, the definition say that is the magnetizing current divided by I1. Yes. From the Ohm's law here, we can say that the from the Ohm's law here, we can say also that the magnetizing voltage is equal to the magnetizing branch multiplied by the magnetizing current. Okay? From there, it's very simple to say that I1 is equal Vm divided by the equivalent impedance, but also it's simple to say that the magnetizing current is the magnetizing voltage divided. Simple to see. Okay, this was what I was trying to explain with few words. I say in my slides that you must notice that the per unit CT error is independent of the primary current, and that is totally true, because if you look over here, the equation alpha, you realize that the per unit CT error depends only on the equivalent impedance, and you must remember that the equivalent impedance depends on the magnetizing branch, but also depend on the leakage, and especially where is extremely important is the burden. The burden is affecting the performance of our current transformer. Okay, Well, let me come back here to my explanation. And okay, here we are calculating now the corresponding ratio correction factor, and then we run a calculation. What if we change the burden? And changing the burden not only based on the magnitude, we also care about if we are using a resistant or if we are using an inductive burden. Okay. Numerical results, I think you can see over there, if the burden is resistive and it's equal to 1 ohm, you can see that the error it's 0.063, but instead if we use a bigger burden, and this is inductive, the error increased to 0.1159. Something similar happened with the corresponding ratio correction factor. If we are using a single ohm, and this is a resistive burden, we get a R, ratio correction factor, of 1.029. But instead we use a inductive burden of J2 ohms, we get a bigger ratio correction factor. Okay, this is the end of this example, but